Hi guys, this is Miss Raina coming to you from C347 here at MacArthur High School to finish up notes about waves and sound. I want everybody to take out the second sheet I've given you that says guided notes, waves and sound. We're going to start on the side of that paper that has the equation box in the upper right corner. So first of all, we're looking at wave velocity. And when we calculate velocity, we've always got distance over time. So what length, what distance do you think we're going to use in the numerator here? And of course, it's going to be wavelength. What about for time? Well, we can use period there. So the time for one cycle is a period. We have another alternative, okay? So if we plug these in, go ahead and write this into your equation box. We get velocity is wavelength over period. Well, what's the reciprocal of the period? It's frequency. So we can multiply by the reciprocal of the period instead of dividing by the period. And we can get this equation. If you haven't already, go ahead and write that in your equation box as well. So here we've got an example. They've given you a rate of 600 wing beats per second. That's telling me how frequently this occurs. And so they've given us the frequency as 600 beats per second. That's 600 hertz. We know that the sound wave is 350 meters per second. And so how do you figure out the wavelength of the wave? Well, we're going to have to divide. We'll take your velocity, divide by your frequency, and you get your answer. So we'll verify that in class since I'm not able to write on your PowerPoint this time. Again, you guys go ahead and take your turn. Try doing the example on your own, and we'll give the solutions in class. All right. So basically, what are sound waves? Just for review, they're little pulses of compressions and rarefactions. So what kind of a wave is that again? It's either the transverse wave that goes kind of like perpendicular to the direction of travel, or it's the longitudinal wave that goes along the direction of travel. And we have longitudinal waves. So make sure you write down this second bullet. It's pressure variations transmitted through matter. And remember, this doesn't have to be air. It can be a liquid or it can be a solid. So a couple of basic properties of sound. Let's see. And we'll just go through these quickly. You don't necessarily have to write them down on your guided notes. But just like in the picture, there's compression and rarefaction. Does this agree with the way we make sounds? Well, yeah. We force air through our larynx. The vocal cords will kind of like relax and contract depending on what kind of frequency we want to put out. In the process, we either squish the air or we allow the air to move more freely, making a longitudinal wave. Okay, here is where you start writing. Fundamental characteristics of sound is the heading. The speed changes only with the air temperature. I can make a high frequency sound or the lowest wavelength I want, and it won't change the speed of that wave. Only the medium has an influence on the speed of that wave. We can hear anything from 20 to 20,000 hertz, and you guys found that out the hard way in class. The loudness is the wave's amplitude, just like think in terms of the amplifier on the stereo. So louder means higher amplitude. And we use something called the decibel system to measure this. Again, make sure you're pausing if you need to write down anything that's going too fast. All right, so again, loudness depends on amplitude. If you want an example, something like 10 decibels would be a whisper, but 110 decibels is what's actually painful to your ear. And again, kind of depends on your own personal anatomy, right? So we'll listen to my favorite song from the 1980s. At one point, the singer hits a note. Some dude thinks it's about, I don't know, a wavelength of 0.14 meters. This is impossible. Help me explain why, quantitatively and quantitatively. Okay, so turn the page over. Let's look at wave behavior and what happens when waves interact. So we've looked at this a little bit when we analyze beat behavior in class. When two waves meet, we have something happening called interference. So let's say we have a positive and a positive coming together. You and me know that they'll add. This is what's called constructive interference, and this is the big vocabulary term that might be unfamiliar so far. So make sure you're writing these down in the blanks. So here are two waves coming at each other. You got a positive and a positive. What's the result? big or positive. Same thing if we have a negative and a negative. Before I was talking in terms of a valley and a valley. What's the result? A bigger valley. Even when they're not exactly the same size. Sketch what you think will happen to the resulting amplitude after we put these two waves together. So here we had wave size 1, wave size 2. What's the result? It's about 3 units high. They're still two separate waves. They're just going to be in the same spot at the same time. Destructive interference is the opposite situation. Now we have one positive or one hill and one negative amplitude or one valley. So predict, what do you think is going to happen when they meet? Sure enough, when they add together, they will produce a smaller amplitude. That's why we call this destructive interference. So if we look at some pictures here, before the interaction, before the interference, we've got a hill plus a valley. There's the hill, there's the valley. The green line you see there is the result. So this is like noise plus anti-noise makes silence. Let's say we've got a little hill and a bigger valley. What's the result going to be? Not necessarily silence, because now you can kind of think in terms of, well, the valley won out. After the interference, the wave continues, so it doesn't die. It's just in that spot, it's interfered with the other wave and kind of canceled it out. So you guys fill this in to your notes and kind of predict. What do you think will happen? Same thing here. In this example, what type of interference did you see? Well, there's a hill and a hill. They come closer, finally they meet, and you guys tell me when we get back to class, did you decide whether this was constructive or destructive interference? Okay, so try this example. Here you've got a valley, and here you've got a hill. They come closer together and they finally meet. There's still a little hill there. So on your own, see if you can explain what happened and decide what type of interference was this. Was this constructive or was this destructive interference? Again, just on your own, use this image to see if you can check your understanding. If I'm adding up waves of two different frequencies, do you think it'll produce constructive or destructive interference? And it matters at what point in time I ask you. So think about your assignment with beats. We've got constructive interference at a bunch of points that I'm seeing now are not actually labeled on the picture. So let's talk about that in class. All right, let's move on with natural frequencies. This is what we were looking at today with the guy who was trying to sing the same pitch as the glass, the lead crystal. So it's an object's fill in the blank with inherent frequency. It's the frequency at which an object will vibrate once it's energized. Resonance is the increase in amplitude when we feed back the object's natural frequency. Resonance is constructive interference happening on that object. So if you guys can think of an example from the video we watched today, you should definitely write it down there. And last question for the next time I see you in class, think about how you would answer, how do resonance and natural frequency differ? All right, thank you guys for sticking with me through this video, and we'll see you tomorrow in class.